11-129 says interstellar space contains mostly hydrogen atoms at a concentration of about 1 atom per milliliter or 1 atom per centimeter cube. We want to calculate the pressure of the hydrogen atoms. Okay, so obviously that atom per centimeter cube is a relationship. Anytime you have 1 unit per another unit, that's a relationship, so we can start with that. The fact that it's hydrogen atoms really isn't significant because we know for gases, the properties of the gases are independent of what substance the gas is made out of. So we want to calculate the pressure. So how do we calculate the pressure? Well, if it's a gas, pressure, the only formula that we really talked about to use to calculate pressure is the ideal gas law. And what we're going to find out today is that the ideal gas law is pretty good, works for most situations. If you have a super cold gas or a super concentrated gas where there's a lot of gas particles in a really small amount of space, then they can start to attract and it might not behave like a gas anymore, right? Because gases, the individual particles don't attract one another, they just bounce off. But in space, the concentration is so low, the molecules are moving around and there's like no molecules around because there's almost no gas there at all. They're not going to really be forming attraction. So we can probably reasonably assume that the ideal gas law should work to calculate correctly what the pressure is. So if we want pressure, we can rearrange this by dividing both sides by the volume. So we need moles, we need R, we need temperature, and we need volume. And it tells us at the end of the question the temperature is 3 Kelvin. Okay, so we should have everything we need, or at least a way to get everything we need. So if I'm going to plug in here, we can start by plugging in what we know we have. We know R always. So R is, I'll leave space for me to plug in the moles first since that was N. But R is 0.08, 206 liter atmospheres per mole Kelvin. I know the temperature is given, it's 3 Kelvin. So I need moles and volume, really, to plug in there still, right? Because I plugged in R and T. So this relationship gives me how many atoms I have in a milliliter or centimeter cube. But if I'm going to use this value for R, I need my volume to be in liters, and I need the amount of gas to be in moles. That's what N represents, the number of moles, not the number of atoms. So I'm going to have to do a couple conversions to get this amount in atoms into an amount in moles, and the amount in centimeters cubed for the volume into a volume in liters. So if I have 1 atom and I have 1 centimeter cube, I have an amount of gas and a volume for that amount of gas. I just need to convert the amount of gas into the right units, and I need to convert the volume into the right units. So how do I convert atoms into moles? Well, in this case, I don't need to treat this as a relationship because I recognize that when I want the pressure, since space should be fairly uniform, if I want the pressure in 1 milliliter, that should be the pressure for any milliliter or for the whole sample of space. So all I need to know is how many moles are in that milliliter, or really what I need to know is how many moles are in a liter. Because if I want to convert the volume to liters and plug that in, I need to know how many moles are in that liter so I can plug the moles in for N. So if I have an atom, I'm trying to convert this to moles. And if I have a centimeter cube, I'm trying to convert that to liter. Right, so for one atom, the conversion I want to do is to use Avogadro's number. That's the number of things per mole of those things. So when I cancel atoms here, I'll have 1 divided by 6.0 22 E23, and that's 1.66 times 10 to the minus 24th moles. So that's the number of moles. So I can plug that in for N up here in my ideal gas law. And the volume for that number of moles is 1 centimeter cubed. But I need to plug that in liters. So if I have 1 centimeter cubed and I want to convert to liters, I would remember that 1 centimeter cubed by definition is what defines a milliliter. And that milli to the base unit is 3 powers of 10. So I need to put that 3 powers of 10 with the smaller unit, set that equal to 1 larger unit. And so that's going to be 1 times 10 to the minus third liters. So I can plug that in for the volume. So the moles cancel, the liters cancel, the kelvins cancel, and my pressure that I'll measure will be in atmospheres. So I would just plug then into my calculator the 1.66 times 10 to the minus 4th times 0.08206 times 3 divided by 1 E negative 3, and I get 4 point, well, really I am limited to 1 sig big by the 3 Kelvin, so I really just have 4 times 10 to the minus 22nd atmospheres. The lower the pressure, which I have an extremely low pressure, the more ideally the gas will be behaving, because the less molecules I have in a given amount of space, the less they're interacting with one another, the more they're behaving independently, which is what makes a gas different from liquid. So if you know you need to use the ideal gas law because you're asked to determine the temperature, the moles, the volume, or the pressure of a gas, start by putting in the information you have and then looking at any other given information, but making sure that when you have other given information, before you plug it in, it has the right units. Right, so the volume has to be plugged in liters, the amount of gas has to be plugged in moles, the pressure in atmospheres, and the temperature has to be in Kelvin.